We'll now use what we know about resolving vectors into their components to solve a whole problem in which we're being asked to add vectors. Here's how we're going to do that. The steps are laid out here, but we'll walk through them using an example. So we're being asked to add two vectors together, vector A and vector B. Let's have a look at what these vectors look like by drawing a diagram. Both vectors are in quadrant 1. Vector A, described here, has a magnitude, this is just the magnitude, which is why there's no arrow above the A, has a magnitude of 25 meters per second. This is an acceleration. So it has a magnitude of 25. What's its angle? The angle for vector A is given here, and it's 16.3 degrees. So we say that vector A has a magnitude of 25 and is directed at 16.3 degrees. So it looks roughly like this. Vector B, on the other hand, is 13 meters per second. A little bit of an excessive fraction line here. It's 13 meters per second directed at 67.4 degrees. So also in quadrant 1, but steeper and shorter in magnitude. So it looks something like this. There's vector B. Again, I've drawn them both in standard position. I'll label this as 67.4 degrees. Looking at the picture, what do we expect the sum of those two vectors to be? Well, using the parallelogram method, sketching in the other two sides of the parallelogram here, gives me a resultant that looks like that. It's still in quadrant 1. It has an angle that's between 16.3 and 67.4 degrees. How do we come up with that number? Well, our first step is going to be to take vector 1, roughly drawn again here, and to resolve it into its x component. So this is the first vector, ax, and into its y component, ay. Now what we're doing is we're adding vector 2, or the second vector, vector B, to vector A. Here I've drawn it, or originally I've drawn it using the parallelogram method. Why don't I draw it using the polygon method down here? So here's vector B. What do the components of vector B look like? Well, roughly, here's the x component of vector B, and this would be the y component of vector B. I notice that if I add up the x components for vectors A and B, I end up with the x component of the resultant. The resultant, of course, will look like this. So we can see that the x components of the resultant are the sum of the x components of the component vectors. The y component of the resultant, again, here is the resultant. Well, the y component of the resultant will be the sum of the y components of A and B. So whether you draw it using the parallelogram method or the polygon method, the outcome is the same. We need to find the components of vector A and B, and then we'll add up the x components of vectors A and B to get the x component of vector R. And then we'll add the y components of vectors A and B to find the y component of vector R. Once we have the components of that vector, here again is vector R. So once we have the components of that vector, this would be the x component of vector R and the y component of vector R. We can use the Pythagorean theorem to find the magnitude of vector R, and then trigonometry to find the angle. Let's do that. All right, how do we find the x component of vector A? Well, the x component is always going to be the magnitude of the angle, 25 in this case, times the cosine of 16.3 degrees. You may just want to punch 25 cos 16.3 degrees into your calculator when we do this, but you could also evaluate this, and you get 23.995. What about the y component? The y component we always find by starting with the magnitude and multiplying that by the sine of the angle. So the sine in this case of 63 degrees. If we evaluate that, we get 7.017. Try the same thing for vector B. Find the x and the y components for vector B. For vector B, we'll take the magnitude 13, I multiply it by the cosine of the angle, cosine of 67.4 degrees, and that gives us 4.996. For the y component, we'll take 13, the magnitude of vector b, and multiply it by the sine of its angle, which is 67.4 degrees. And that gives us 12.002. So that was step one. We've resolved vectors a and b into their x, y components. So now we want to find the x component of vector r. So we'll take the x component of vector a and add the x component of vector b. So that gives us an x component of the resultant of 28.991. Here I'm just adding the two decimal numbers. Another way to get to 28.991 is to simply add 25 cos 16.3 plus 13 cos 67.4. That means I don't have to write down any intermediate numbers, and I don't have to worry about making any rounding errors or keeping enough decimal places in my intermediate steps before rounding the final answer. So here I'm showing you the numerical evaluations of these and how I would add these numbers. But generally when I do this, I simply add that expression in one shot using my calculator. In any case, once again, taking 7.017 and adding 12.002 gives me the y component of the resultant, and we're told that's 19.019. So now we know that the x component is 28.991, roughly 29, and the y component is 19.019. Given the components of a vector, we can now use the Pythagorean theorem to find the magnitude of the vector. The magnitude squared will be equal to the x component squared and the y component squared. We can save ourselves a bit of time by immediately taking the square root of both sides. We'll take the square root of r squared. The square root of r squared is just r, and then of course the square root of the right-hand side. So we find that r is equal to the square root of 28.991 squared. Drop that in brackets, even though it's a positive value, just in case. Sometimes the components, of course, for x and y can be negative. And then we'll add the square of the y component. That's 19.019 squared. Dropping all of that into your calculator, you'll find that the magnitude to one decimal place is 34.7. So the magnitude of the resultant is 34.7. Which I don't think is unexpected. We expected it to be longer, based on our picture, than either vector A or vector B. But what about the angle? To complete our answer, we have to give both parts. We have to fully describe a resultant vector, which means we have to give both its magnitude and its direction. Looking at this right angle triangle that we've drawn with the resultant and its components, this makes me think of using tangent. The tangent of an angle is y over x, opposite over adjacent. So the tangent for our resultant will be the value for the y component divided by the value of the x component. So of course, taking the inverse tangent of both sides gives me this answer. Now I recommend here for this particular exercise that you take the absolute value of the ratio. Essentially what we're looking for here is the reference angle. In this case, because we can see that our resultant is a quadrant 1 angle, it doesn't matter whether or not you choose to use the absolute value here. But there are certainly other problems where this will come into play. So we've got 19.019, that's the y, divided by 28.991. Tricky to push this all into the corner of the slide. So taking the inverse tangent of that ratio and rounding to the nearest tenth, we get 33.3 degrees. So we should summarize this. So therefore, the resultant vector, using the same notation as is given in the question, has a magnitude of 34.7 units. What are our units? They're meters per second. And it's directed at an angle of theta is equal to 33.3 degrees.